basically.
Okay.
Dude, should I share the screen now?
Yeah,
Wait, sir, wait, sir.
Dr. Raja will first introduce you, and later, after he finishes, you can.
Sir, put it full screen, sir. Yeah.
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 Raja, sir. Yeah, you can start now.
Yep. So can you see it now?
No. Raja, sir.
Yeah.
No, Dr. Raja.
Hello.
So,
So good evening to everyone, and good morning to Yuri. So the next talk is going to be given by Dr. Yuri Gogosti from Drexel University, United States of America. So it's my great pleasure to just introduce about Dr. Yuri Gogosti. So he is a professor at Drexel University, and he is leading a nanomaterials group at the Department of Material Science and Engineering. And Professor Yuri Gogosti was a part of the team that discovered MXene. It's a new family of 2D materials. So currently he has more than 100,000 citations to his credits as per Google Scholar. He is the recipient of several prestigious awards and prizes. Recently, he received an International Ceramic Prize, the highest honor conferred by the World Academy of Ceramics. His research interests include synthesis, surface modification of inorganic nanomaterials such as nanodiamond, carbon-derived carbons, nanotubes, and two-dimensional carbides and nitrides, nothing but MXenes. His area of study are material science and engineering and nanomaterial. I just welcome Dr. Yuri to just deliver his talk on MXenes for wearable technology. Thank you.
Okay.
Yeah, you can share your screen.
Let me share my screen now. Can you see my screen?
Yes, perfect. Yeah.
Very good. Well, good evening, everyone in India. Good morning to people in the United States. And good day, good evening to everyone else, depending on where you are. It's really my honor and pleasure to speak to an international audience in this conference. And I understand it's quite late in India and elsewhere in Asia. So thank you to those of you who stay awake and listen to presentation that I'm going to deliver. Also, I would like to thank Professor Grace for giving me this opportunity, and thank to Dr. Raja Salapan for introducing me. Just like a half a year ago, I visited Vellore speaking at the conference at Vellore Institute of Technology, and it was a really great experience. However, in the past half a year, a lot of things change in this world. It looks like a different age, different time. We speak, communicate online. And also along these lines, I want to talk about wearable technology, internet technology, something that allows us to stay connected, even if we cannot be physically close to each other. So I'm going to talk about a new family of materials called MXenes. It's relatively new, actually was discovered almost 10 years ago by now, but it's up and coming quickly. And I will focus on application in wearable technology in smart textiles. And this work is largely based on research by my two PhD students, Simge Uzun and Ariana Levitt. Ariana actually just graduated from Drexel University with a PhD degree, and Simge is going to graduate later this summer. So, what are we studying and why? You all use internet. You are listening to my talk now online, whether you are using Zoom or YouTube. And we get not only people, we get also devices, items around us communicating to each other. Internet of Things is growing very quickly. More and more items in our daily life, in our homes, our cars, become connected. What it means that we will have lots of devices needed for continuous communication. And many years ago, people started with huge computers, which were occupying entire rooms. And there is a famous joke that a person in IBM told that she would wish to have a computer at home. Later, everyone got a computer at home. Then we moved to smaller computer, from desktop laptops, later to smartphones. Pretty much, I'm sure everyone listening to me has a smartphone, almost everyone, in addition to a computer. So what is the next stage? What is the next step in development of these technologies here? Many people believe that actually all this computing power and more sensing, communication abilities will be incorporated into textiles, into devices that will be wearing. It may be textile, it may be a skin tattoo, it may be some other devices like already available, for example, smartwatches, but there will be stuff we will probably wear with us. Something which is more convenient, that a pretty bulky, say, smartphone that I have and many of you have, and sometimes struggle to find where to put it in our pockets here. And why textiles are great? Because they cover our bodies. Everyone wears some textiles. No one walks naked, even though you can enjoy maybe watching me speaking about MXenes, even sitting naked in the comfort of your apartment here. And actually, textiles are present in our life all day around, 24 hours, wherever we go. Maybe expect of a sauna here. So if we can incorporate our communication, sensing ability into textile, we will increase comfort, mobility, and this will probably be the next step really in communication technology here. But what do we need for this? We need to have actually smart textiles. We need to have devices made in a different way, not placed in a box like a smartphone, but being distributed within textiles we wear here. And nanomaterials provide one of the ways of doing it here. You have heard a talk by Andrew Geim, who discovered exciting new physics in monolayer graphene together with Kostya Novoselov. And graphene boom led also to kind of a rediscovery of some other two-dimensional material like boron nitride, moly disulfide, and other transition metal, dichalcogenides, which have actually been studied for a long time along graphene, and also to discovery of new materials in a two-dimensional state. People produce two-dimensional metal organic and covalent organic frameworks, silicene, borofin, germanine, and in 2011, we published on discovery of a large family of two-dimensional materials called MXenes. And I will talk about them and extend why they are unique, because they are, many of them at least, most of them are true metals with a high density of state at their Fermi level. So they greatly add to semiconducting and insulating materials, making majority of other two-dimensional materials. They're atomically thin. If we want to make wearable nano devices, we need materials which are capable of taking any shape, often optically transparent and highly flexible. And also, with a large lateral size and small thickness, these materials have high specific surface area. So they're capable of doing many things, from electrochemistry to sensing, adsorption, or catalysis. So what are those MXenes? Why do we call them this way? M stands for like titanium, moly, zirconium, hafnium, tantalum, and others. X stand for carbon or nitrogen. So basically, those are two-dimensional carbides or nitrides of transition metals. They belong to several groups that call M2X, means two layers of transition metal, one layer of carbon and nitrogen between, M3X2, three transition metal, two carbon nitrogen, and so on. Moreover, we can make not only stoichiometric compounds, of which about 30 has been reported now, but also solid solution when we can mix randomly M elements or X elements. And as a result, we have an infinite number of composition possible. But we can also put atomic level engineering to a next level, making atomic sandwiches, double transition metal MXenes with one layer of elements, for example, moly on the surface, and another, for example, titanium in the middle, making something like moly to titanium C2. And colleagues in Sweden and Linköping University, led by Johanna Rosen, showed that also it's possible to make double transition metal MXenes where monatomic columns of one element alternate with two monatomic columns of another. And if you etch these columns like yttrium or scandium, you can get ordered divacancy MXenes. And advances continue. Just like a few months ago, in the beginning of 2020, we published a paper showing that we can expand the family of max phases, precursor for MXene and MXenes, to a next level. When we have 5 atomic layers of transition element connected by 4 layers of carbon. And I'm sure there are many more materials to discover. So far, we believe more than 100 of stoichiometric MXenes are possible, and infinite number of solid solution, making these materials easily potentially the largest known to us family of two-dimensional materials here. But there are many different materials known. Whenever we bring something new to the table, we need to think, okay, is it useful? Does it give us something different from other materials? And I already stressed conductivity. It's very important because even in these thick films where we line up thousands of MXene flakes in thickness, we can still get 10 to 20,000 Siemens per centimeter conductivity, which is roughly an order of magnitude higher compared to, for example, famous reduced graphene oxide films, which are widely used as conducting layers, conducting films here. They're also very strong and stiff. Single layers of MXenes have strengths of 20 to 30 gigapascal, and Young's modulus between 300 and 500 gigapascal, which puts them to a very strong materials group. They inherit their known extremely strong and hard transition metal carbides and nitride. But what is also interesting, they are hydrophilic. They can be dissolved in water because of their wet chemical synthesis. They're transparent in this film, and also if we talk about textiles, they come in a variety of colors, unlike graphene, which brings you all shades of black. They're dispersible in water, can be printed from aqueous solution, no additives, or we can use this solution as dyes for dyeing textiles and give them electrical conductivity and also a variety of other properties here. Plus, there are many other useful properties, like they can be heated by light, different wavelengths, depending on properties, because of plasmonic materials. They absorb electromagnetic waves. They can protect your credit card in your pocket from being read by someone else here. And they can be used as materials in battery supercapacitors because of their electrochemically active surfaces. So they look like conventional two-dimensional sheets. They're crystalline, they're single crystals actually. This is about 20 micron single layer titanium carbide flake you can see here. And we can make them into films and variety of different things. It's natural to compare them to graphene, the most known member of the family of two-dimensional materials. Moreover, usually if we talk about fibers, textiles, films and coatings, people use graphene oxide, which is often after that reduced to produce reduced graphene oxide to make it conductive here. So MXenes are hydrophilic and water soluble because of high zeta potential, negative zeta potential, like graphene oxide. But after drying, without any kind of a further reductive treatment, high temperature treatment, they're actually more conductive than RGO films. They're stiffer and stronger actually, compared to both GO and RGO. And actually, MXenes are more transparent, has a higher figure of merit compared to reduced graphene oxide. So it's naturally exciting to use those materials, their variety of properties and colors, which are tunable in this very large system to produce different devices here. Moreover, in many applications, for example, energy storage, we combine different materials. MXenes complement other materials available, like graphene, like transition metal oxide, transition metal dichalcogenides. So we can use two-dimensional materials as building blocks to build devices, systems, metamaterials with properties which no single material can give us here. Let me just step back for a moment and talk also about synthesis, how we make those materials. So you know already that MXenes contain one of these elements from this system M element, marked yellow in the periodic table, and carbon and nitrogen X. Most cases, as precursors, we used MAX phases. This is a family of layered ceramics developed by my colleague at Drexel, Professor Michel Barzooms, over more than 2 decades. And what we do, we etch away an element from this system, and we end up with M and X only. So this is actually how the name MXene came out from. There are other precursors. Layered carbides were aluminum carbide layers, for example, or 2 layers of gallium connect layers of Moly2C or zirconium 3C2. So basically, we start with a layered ceramic, we etch away monatomic layer, aluminum, silicon, gallium, others, and we end up with this type of structures looking very much like vermiculite clay or thermally expanded graphite. We disperse it, delaminate, and get single flake in solution or in a film. What is also very important. Of more than 200 two-dimensional materials reported today, only very few can be produced in any significant quantities. Graphene, boron nitride, clay. And MXenes is actually one of them. Because of the wet chemical synthesis, currently we have a reactor developed by, for us by Materials Research Center in Ukraine. We can make 50 grams, it's a 1 liter reactor, can push it to 100 grams per batch. There are already 1 kilogram per batch setups in industry, but potentially there is nothing preventing you to build a 100 kilogram or 1 ton reactor for synthesis when the market justifies it here. Moreover, we can not only make titanium 3C2, which I showed you in a previous picture, the most common first discovered MXene, but also these more exotic materials. For example, this sandwich-like structure mentioned. One of very important properties of MXenes is their solubility in water. So we have a colloidal solution with about -30 at 7 or -40 millivolts the potential at neutral pH. As a result, we can disperse this material as water without adding any surfactants or additives. So as a result, if we process this material, we don't need drying, we need drying, but we don't need any burning of binder. And we can separate flakes into different sizes and produce different fraction of particles, or we can start with particles of different sizes here. Of course, for some of the processes, for example, making composite materials or else, we may wish to use polar organic solvents, and transfer the material from water to polar organic solvent here. However, whatever you use as a solvent, you can after that use a variety of coating techniques: spray coating, spin coating, dip coating, inkjet printing, doctor blading, 3D printing to make films. Printing, for example, conducting patterns, making transparent conducting coating on glass, making transparent devices, for example, like this micro supercapacitor with outstanding performance exceeding that of conducting polymers, nanotubes on graphene here. But the key advantage is really comes when we use those type of materials in wearable and flexible devices here. So I already mentioned pretty much this is a property of any very thin materials. Here you can see, for example, an interdigitated device. This was a supercapacitor on a flexible, transparent film. We can make also actually dozens of devices like this work done in collaboration with KAUST in Saudi Arabia shows, making devices actually capable of AC/DC conversion, showing a phase angle close to 90 degrees in a wide frequency range, and they are fabricated in a silicon chip, so it can be used in electronics. But we can also transform them into wearable and make these devices embedded in textiles like this interdigitated pattern shows here. India is one of the leading manufacturers of conventional textile in the world. But I can envision in the future, India also taking a lead in smart textiles, moving from conventional wearables to smart textiles, textiles that can sense, respond to changes in their environment here. And they are convenient to provide in safety when you walk or ride your bicycle or a bike on the street here. They can be embedded actually not only in wearable, but also, for example, in your sofa, that you can have control of your home electronics just on the side without having a separate device, which we always try to find where is our control, which is get lost in the room here. It's certainly needed for first responders, for military that look for safety in the environment, need to communicate to each other in extreme conditions here. So we can make textiles which will provide illumination like LED lighting, touch sensors, also energy harvesting here. What is also actually the key factor and key issue with realizing many of these things that are already available here is storage of energy. Currently, whenever people develop smart textiles, in most cases, energy storage is done by using a separate battery, which appear to be bulky and maybe actually the largest component here. What we are trying to do in my research group is also build nanoscale, not nanoscale, but new generation, flexible, multifunctional, wearable devices utilizing nanomaterials. And actually, MXenes are materials which offer new opportunities in the field. They have already been tested in a very large variety of electrochemical energy storage, also other electrochemical systems like electrocatalysis or electrochromic materials that change their color as applied potential. Why is it possible? Because MXenes on their surface have transition metal, which is terminated by oxygen, OH, fluorine, chlorine, other elements that are present in the etching solution. As a result, the surface of MXene looks actually like the surface of a transition metal oxide hydroxide, materials traditionally used electrochemical capacitors or batteries. The transition metal on the surface can change its oxidation state, can be reduced, for example, by changing oxygen termination to OH or oxidized. As a result, we have a battery-like behavior, but without solid-state transport limitations here. And they have been used in a variety of different systems, but I will particularly talk about pseudo-capacitive energy storage today. Energy storage when we use redox reactions on the surface, but without solid-state diffusion here. I trust many of you listening to my talk are a specialist in textile materials, but certainly some of you probably not here. You may be working in two-dimensional materials, nanomaterials, or another topic. Let me very briefly introduce you. What are the components of the fabric? So because we're trying to embed our materials into fabrics here. We start with a fiber. There can be natural fibers like cotton. There can be regenerated fibers, rayon, or synthetic famous nylon fiber here. From fiber, textile industry people move to yarn. For example, this is two-ply yarn when two fibers are combined together, and then yarn can be further transformed into fabric, which can be woven, can be knitted, or produce other techniques here. So if we want to incorporate materials for energy storage or sensing or other application, we can approach in two ways. Typically, we can either embed it into fiber, coat the fiber, or have it inside the fiber, or we can take already produced fabric and print it or dye the surface of the fiber. Same way as, for example, logos or a picture of your famous sports team mascot or a rock band can be imprinted on a t-shirt here. So, we need to produce yarns, and we can also do it at that stage by coating the surface here. And the simplest process is actually take solution of MXene I showed to you before and deep coat yarn or cotton fiber, which is non-conductive. All of you are familiar with it here. Just simply run it through a bath with a solution of MXene particle. As I already told you, MXene forms stable colloidal solution in water, so you don't need to add anything. These particles will coat or infiltrate MXene and, infiltrate cotton, giving it conductivity. Moreover, what we observed that we can take small flakes. It means that flakes which are hundreds of nanometers in size, like a 300 nanometer average. And those flakes will go very deep into the fiber, covering the surface, giving everything in. But if I take larger flakes, which are micron size or larger, they actually will form a sheath on the surface. Yeah. And of course, conductivity will change, and actually it will be sufficiently good, more than you get in many conducting fibers. But if you combine both approaches, it will be even higher. And in this case, we can go to hundreds of Siemens per centimeter, which is sufficient for majority of application because we have infiltrated fibers and after that coated additionally with large MXene flakes here. So this type of a textile is very easy to produce. It doesn't really require anything special here. It's the same dyeing system as is used to change color of current material. And you can do it in entire fabric. But for most application, you want to have patterns knitted or woven into the fabric and textile. But again, this is a scalable and commercial process here. And let me try playing this video for you, if it works. It did work for me yesterday. Okay. So this is how knitting works. I have a colleague at Drexel University, Professor Genevieve Dion, who leads the Center for Functional Fabrics. And they have these machines which you can program. And you can basically knit any pattern you want using this machine. You can basically make devices. So it's a high-tech process becomes. We pretty much create textiles. We program the pattern we want, and then we let machine knit it for us here. And you see also, depending on how you knit it, whether you use single jersey, half gauge, or interlock knitting, you get different pattern with different density. And actually this interlock knitting shows the best performance. And you can see MXene coated fibers forming a nice and dense pattern here. And this is what we can use for further application. Moreover, what is very important, whenever someone talks about textile, and especially smart textile, the first question that comes, is it washable? Is it possible to use the fabric the same way we use? Is it biocompatible? Is it, can it irritate the skin? I don't have time to cover everything in this presentation, but many independent studies in different countries showed that MXene, titanium carbide MXenes at least, are fully biocompatible, non-toxic, and can be used in wearable applications. Here, moreover, also can be even implanted or used on skin directly here. But what is also important here, you can see here 45 hours, many washing cycles, and you see there is a very small increase in resistance only after this cycles, even going to 80 degrees C temperature. So it means that we get washable textile with MXene still staying on the fibers, showing very high stability, very small loss of MXene. And that's actually important because we get now textile, which is highly conducting. But for example, when people use silver to coat it here, in many countries, it's not allowed anymore to use silver because silver lost during washing cycle, goes in water stream, killing microflora in rivers and lakes here. And with MXenes, we can be safe because, for example, titanium 332 will only produce titanium dioxide and carbon gaseous products, which are much safer materials. Moreover, if we measure conductivity of these fibers as a function of length, you will see a linear dependence. This is cotton, bamboo, linen, different type of fibers. What does it mean? It means that the fiber has same conductivity along the length. So there are no cracks, no breaks of the circuit. So if you need a long thread, which acts as a conductive wire in a textile, you can do it and you can produce it again based on conventional cotton materials. Things here. And actually, MXene coating even increases mechanical properties, strength of these fibers. At the same time, it doesn't make it much stiffer. So textile is still comfortable to wear. And we use, for example, the specific fibers as supercapacitors, as pressure sensors. I will give here this example, and I will give you an example of use for energy storage application, supercapacitor on a different type of fiber here. But you can see basically that gentle, moderate, hard touch of the finger on this sensor embedded here can be very easily distinguished here. Now, I gave you an example of taking a very conventional cotton or other natural fiber and transforming it into conducting fibers that can be used in smart textiles. However, what if I want to make a pure MXene fiber with an order of magnitude, at least, higher conductivity, with properties that only like a pure MXene can give to us, because we'll have much higher loading. If we use it, for example, for energy storage, we'll store more energy compared to in a coated fiber textile. And we achieved it by using liquid crystalline MXene. Actually, in 2011, working with Professor Shu Yang, we showed that MXene can form liquid crystal structures, but we added surfactant actually acting as a liquid crystal and helping to align MXene flake. However, more recently, working with our collaborators at Deakin University, Simge, my PhD student, showed that depending on the concentration of MXene flakes and their size, it's possible to move from isotropic dispersions to biphasic and at high concentration, even nematic phase liquid crystalline. So what does it mean? That all flakes in a dispersion like a clay align relative to each other. And you can see for large flakes, you achieve it at smaller concentration. For smaller flakes, you need a higher concentration. This work was published in ACS Central Science in February and made it on the cover of this journal. What we can do with this liquid crystal MXene, we can also draw fibers, pure MXene fiber, just injecting them in the coagulation bath. And you can see here collected fiber. And this is a skin electron micrograph, and you can see you can tie a knot on this fiber here. So taking flakes of different sizes, as I mentioned to you, we can control their rheological properties and achieve properties that we need for flakes. And we can control those properties by controlling size of the flakes and concentration of the material here. And we see that pretty much gelation is possible in both types of a solution here. We have elastic modulus higher than viscous modulus in these solutions here. And this is what allows us to draw these fibers. And depending on type of coagulation bath, we can also control density of the fiber. For example, the chitosan bath, we will have much denser fiber. What it means, higher conductivity, but lower permeability. With, sorry, let me just get back. With acetic acid, we get looser fibers because there's a slower coagulation process somewhat here. And we can make fibers for sensing applications, for energy storage, many others. And as you can see, conductivity actually can approach 8,000 Siemens centimeters. So we talk not about 100, we're already talking about 1,000 Siemens per centimeter in this fiber, which is extremely high value. And also we go to density, which is very high in case of chitosan based fibers, independent of flake size here. So that's very important. We can control density and get extremely high value of conductivity per gram for these materials here and sufficiently good strength. Now let me talk very briefly before I wrap up about electrochemical properties of the fibers. What you see here is a cyclic voltammogram of the material produced in aqueous protoelectrolyte. And it is actually a combination of a double layer capacitors, which would be a rectangular CV, and a redox process that happens as shown in this broad but very symmetric redox peak on the surface. In case of aqueous protoelectrolyte, we cannot go above 1 volt roughly voltage window because we start producing hydrogen, so we can limit it here. But we can have another electrode, for example, reduced graphene oxide or conducting polymer or another MXene, which will give us wider voltage window, more energy stored here. But these liquid crystalline fibers show a very good behavior. We see volumetric capacitance, which reaches to 13,000, 1,300 farad per centimeter cube. This is extremely high value, 5 to 10 times larger compared to can be produced on carbon fibers, porous carbon fibers under this condition. And you can see that conductivity is very high, also ionic conductivity with almost vertical Nyquist plot, and also very low resistance of these fibers here. So basically we can get a good material for electrochemical energy storage. But we can use those conducting fibers also for resistive heating, or we can actually heat them by simply near infrared radiation at 780 nanometers, like a red diode laser, because, for example, titanium-32 will be absorbing in this range here. And we can also use this material to make antennas, because titanium-32 is an extremely good material for antennas showing attenuation lower than even majority of metal, actually very close when you make practically sized antennas to copper here. Or RFID tag, which will allow you to communicate with other devices, enabling Internet of Things here. Or, as I mentioned in the very beginning, we can make electromagnetic shielding devices, and MXene show extremely good EMI shielding behavior. And moreover, you can see all these materials lined up here have variety of different colors. Those testing were done on thin film on no fibers, but you can do the same thing on fiber, protecting people working at high fields, for example, next to radars, or protecting your credit cards or smartphones from being accessed by someone else when you put it in your pocket here. So to summarize, as I'm coming towards the end of my publication presentation here, we can use two-dimensional transition metal carbides, nitrides to produce textiles. We can coat conventional natural textiles like cotton, linen, bamboo with MXene, transforming them in conducting wires. But moreover, wires were high surface area that can use for energy storage, sensing, many other applications. We can do same thing with nylon and other synthetic fibers. MXene sticks very well to nylon surfaces because of nylon positive surface charge on nylon here. And we can also make pure MXene fibers by either by scrolling with carbon nanotubes or drawing from liquid crystalline solution of MXene flakes. Again, let me stress, we did not have any surfactant, any additive, any binder. No burning of the binder was required to achieve this 7,000 to 8,000 Siemens per centimeter conductivity, just drying the fibers. And we can use them in addition to energy storage devices, supercapacitors, antennas, strain sensors, actuators, electromagnetic shielding, many other different applications here. So MXenes are really picking up speed. I showed you a very, very small subset of research we are doing on these materials here. But there are about 1,000 institutions, if you search papers published in Web of Science from 87 countries that already published work on MXenes. More than 1,000 patents in Google Patents here. I talked today about titanium 3C2 MXene. It's a great material. And one of the reasons it's great because it's highly conducting, but also it contains titanium and carbon. And T stands for this oxygen, OH, or other surface termination on the surface. So they're all abundant, inexpensive, environmentally friendly elements. And it means that this material that can be produced scalably in larger quantities has a real potential of application. But what is also important, only 1/3 of all the papers published deals with all other MXenes. And as already mentioned, there have been more than 30 stoichiometric MXenes and dozens of solid solutions reported so far. And dozens more of stoichiometric MXenes and unlimited number of solutions possible with other elements. They can give us other properties, including all these different colors I showed you today, but also different chemical, electronic, other properties. And there are many applications going beyond energy storage or sensing, I mentioned to you, including filtration materials. Some MXenes have been shown to be bactericidal, can protect us, maybe coating a mask, killing viruses and bacteria. They can be used in gas separation, water filtration, biomedical application, electrodes, cancer treatment, dialysis, absorption of urea, and optical applications for also sensing that can be done in textiles with source lasers, photo detection, and others here. So this is a growing, booming field with potentially many interesting applications. And of course, we're still in the beginning of the road. Much more work is needed here. Before I finish, I wanted to thank my research group. This as our students last year at a summer party in backyard of my home. We're still in quarantine. I'm still speaking from my home. And I hope that by the end of the summer, we will be able to come together and celebrate in my house with my group here. Thanks also to former students, postdocs, visiting scientists whose work are used in this presentation. We have many, many collaborations around the world. I listed some of them. This is list is far from complete, but I specifically wanted to stress Professor Genevieve Dion, with whom we work on developing smart textiles, and also Professor Jo Razal from Deakin University in Australia, who is our collaborator in particular in MXene fibers and textiles. And much of the work I showed you today was done in collaboration with two research groups. And we enjoyed funding from a variety of sources. Before I finish, I wanted you to show two more slides. One is that there will be a conference on MXenes in China, in Ningbo, in October 11th, 14th, 2020. It was initially planned for May. Last year, it was second conference was in May, bringing together about 450 scientists in Beijing, and it has been rescheduled for October, so you may be able to attend. But we will also have a conference at Drexel University in August, even earlier. And actually, it was also planned to be on campus, but we moved it to a completely online event. And we also will have courses of synthesis and characterization of MXenes before this conference. So if you're interested, either learn how to make MXene, how to do proper characterization, please check the website of the conference and register for courses at the conference. Conference attendance is free and there is nominal charge for the courses. And also, if you want to read more about MXenes, we published a book last year, which is written, actually has chapters written by leading experts in the field and the best way to start in the area here. Thank you very much for your attention. I'll be glad to answer questions.
Thank you, Dr. Yuri, for your enlightening talk on MXenes. So we have received a lot of questions from the participants. I will just ask a couple of questions. The first question is from Shreya Soy. What about the adjacent property of MXene on textile? And what is the lifetime of such textiles for real-time application?
Can you repeat the beginning of the question? What about what kind of properties?
What about the adhesion property of MXenes on textiles?
Yes, thank you. So the adhesion depends on the textile. As I mentioned, we try to use just water to avoid any kind of toxic solutions, and they very well infiltrate and stick to the surface of bamboo, linen, cotton, other natural fibers simply by hydrogen bonding because of oxygen OH on their surface. They also stick well to the surface of synthetic fibers like nylon containing positively charged amino groups. But for example, and they have a really excellent adhesion. As you see, many washing cycles after drying are possible. However, if you take, for example, polyethylene or polypropylene fibers with the surface which is not which will not adhere to MXenes, you will have poor adhesion. So definitely you need to think, but luckily again, for majority of natural fibers, it really is great and works very well. And lifetime, as I showed you, we can go up to dozens of machine wash cycles. What will be the lifetime? We know in films, at least for years, there are no significant changes in the material behavior. Whether it will be the same, how long under sunshine and other environmental factors, this is still to be studied.
So the second question is, you said that MXene is water soluble. On the other hand, you also mentioned that the developed textile is also washable. So is there any intermediate curing which prevent it washable after coating on textile?
Yeah, that's basically a good question. I didn't have time to explain many details. So single separate particles after delamination, they form stable colloidal solution with a high negative charge on the surface. But when you infiltrate fibers, make a coating, and multiple flakes of MXene come together, they restuck. If you dried them and remove water between the layers, they form bridges between the flakes. And after that, you cannot redisperse them again. You will have to again intercalate and delaminate them to break flakes off. So you have to do good drying after coating, and then it becomes not more soluble in water.
So another question from Himadri. So he is working on capacitive energy storage devices, and he is planning to work with MXenes. Due to the hazardous behavior of HF, and they are not able to use HF for etching. So could you please let me know about the safety issues of LiF lithium fluoride plus HCl based etching of A metals?
If I understood the question correctly, the challenge is using HF. In the very initial study research in MXene, we used pure HF solutions up to 50% HF. But first, you can go to more benign, much lower concentration. 5% is sufficient for etching. Second, what we are doing now for larger scale synthesis majority, we use much less dangerous acid like hydrochloric acid, HCl, and metal fluoride like lithium fluoride, or you can use also sodium fluoride and other fluoride metals potentially. And as a result, we avoid using dangerous HF. Also, there is much lower content of fluorine on the surface. However, the group of NIN at NINBO, the one that will be organized in the third international conference, they developed process which doesn't include HF, using molten salts, replacing aluminum with zinc, and then HNC and HCl. So there are processes, read in the literature, even in the book, that don't involve using HF for synthesis.
So thank you. Another question is, how could this MXene be usable for making protection suit for hospital or as a simple mask considering the current COVID-19 situation?
Well, there are a couple of different things. One, as I mentioned, a number of two-dimensional materials actually have been reported to have bactericidal properties. So potentially it's necessary to show whether it also will be antiviral. But one of the things is possible, and definitely possible. MXene can be heated by near-infrared light to temperatures that will be sufficient to kill viruses, bacteria. So for disinfection, it's possible to use not only UV, but also infrared radiation for removing virus on the surface. However, we actually have another COVID-related project. Many with MXenes, many patients after being admitted to intensive care end up with acute kidney disease, damage done by consequences of COVID-19. And MXene is actually the only sorbent for urea. So what we are trying to do is to develop portable systems for dialysis and also improve the current dialysis system, because hospitals experience problem in providing dialysis to COVID-19 patients here. So we always think how we can basically use new materials to solve problems that society is facing. And this is definitely COVID-19 is one of the most challenging problems everyone needs to work on.
Thank you. Another question is how to prevent the surface oxidation of MXene during the synthesis?
How to prevent oxidation?
Surface oxidation, yeah.
Yeah. Again, monolayer of oxygen or OH on the surface. This is exactly what makes actually MXene environmentally stable. So we want oxygen to terminate transition metal, because transition metal atoms will not stay in the environment unterminated anyway. What we don't want to have is formation of metal oxide excessively. It will decrease conductivity, also decrease environmental stability. Initially, materials we produced years ago had fairly limited oxidation stability, at least in solution, colloidal solution as single flakes. Materials we develop now and produce can actually stay in deaerated colloidal solution, even without refrigeration, for months. However, as soon as you have produced a film, and this film has been very well dried, there is no water, no excess of air and water between the layers, those films are very stable. We have films of MXene laying in drawers in our lab without special protection for now years, and they typically maintain their physical properties. Colors, conductivity may decrease by a few percent over a year, but they become stable after that. And of course, it depends on composition. Some thicker MXene, as a rule of thumb, like titanium 3C2, tantalum 4C3, are more stable than thinner one, like titanium 2C or V2C in solution.
Thank you, Yuri. One more last question. Max phase synthesis requires high temperature, approximately 1300 degrees Celsius. How effective is molten salt technique in reducing this temperature for synthesis?
Well, again, we don't work on this process ourselves, but the group done in work done by a group in China shows that the synthesis seems to be quite efficient. It's possible to do it at somewhat lower temperature. It's possible to do it under molten salt without having vacuum furnaces. So it looks promising. Let me also remind you, there are also other inexpensive methods for max phase synthesis, like self-temperature, high temperature self-propagating synthesis. So definitely, while we can produce MXene in large quantities easily, we also need to decrease the cost of max phase precursor. So one of the important research direction is working on synthesis of precursors for MXene max phases directly from ore, directly from very inexpensive minerals, and then we will have also inexpensive and widely available MXenes.
Thank you, Dr. Yuri.
We can stop the session. Thank you, Dr. Yuri, again for the excellent presentation, and the participants were really enjoying your presentation. And for for the sake of time, we have just asked a few questions. There are a number of questions posted by the participants. So, on behalf of VAT, thank you once again, Dr. Yuri, for accepting our invitation.
It's my pleasure. Thank you very much for inviting me and giving me opportunity to speak.
A privilege. Thank you, Yuri. Yeah.
Goodbye, everyone.
Yeah, goodbye. Have a great day.